Hello, welcome everybody to my talk on our Clarity Challenge 2021 submission, where we present a cascaded speech enhancement for hearing aids in noise-reverberant conditions. I'm Chen Xi. Let me give you a brief outline. First, I will introduce scenario model and motivations. Second, the proposed system with system overview and more details on the modified DCCIN and dynamic equalization. In the third part, I will talk about the evaluations on challenge data. Finally, give a brief conclusion. For the challenge scenario, clean speech and point source noise are both convoluted with the corresponding room impulse response. Then scale reverberant noise to achieve desired signal-to-noise ratio mixture speech. Therefore, we have to design a speech enhancement system to improve the quality perception of hearing aids devices. In this scenario, several challenges from real-world application are considered, largely varying noise types including speech noise and non-speech noise. Signal-to-noise ratio ranging from -12 to 6 decibels. Reverberation varying from different room conditions setting. These settings are enhanced for hearing aids users, rather than normal hearing listeners. As a solution, we propose a deep learning-based denoiser that can overcome varying noise environments. As a second part, we introduce a signal processing-based de-reverberation. The last point, we use the equalization post-processing to improve listening perception for hearing impairments. The second part. Let's focus on the system overview. These three equations describe the signal model of the scenario we talked before. Modified DCCIN applied complex maskers on the short-time Fourier transform to subtract reverberant noise from mixture speech. Then narrow WPE is applied to decompose reverberation from S hat HT, where the iteration time is set to 3 and channel set to 1. For the objective matrix, S hat T is processed to official hearing aid simulator and hearing loss simulator to compute modified binary short-time objective intelligence score. The baseline hearing aids processor is based on the Cambridge feeding strategy for a specific listener's audiogram. Hearing loss simulator simulates spectral smurfing and lawless recruitment according to individual hearing loss severity. For the subjective listening test, we employ dynamic equalization to improve listening perception. DCCIN operates in the STFT domain. It uses 32 milliseconds frames with 20 milliseconds hop between windows. Looking at the diagram, the input noise reverberant signal is processed using STFT. We use the time frequency domain information for future extraction, then go to a modified DCCIN model. It produces the output reverberant complex spectrum, on which we apply the inverse STFT. So, the key elements I'm going to talk specifically about here are the causal system, relatively lightweight neural network, the complex spectrum maskers, and the joint loss function. For the causal system, no zero padding is required on the convolution layer, halved hidden units in the LSTM layer, and removed dense layer. We can train a relatively lightweight neural network. The key idea behind the DCCIN is a complex spectrum maskers applied in magnitude and phase. Even with the complex maskers, some bands, especially when in low SNR, can still sound noisier. So the solution to that is to de-emphasize these noisy bands and to emphasize clean bands. This is inspired by the post features for the self codec. This idea here is to apply a nonlinear function to the gains related to the magnitude maskers we compute. Then, we normalize the results to boost collinear bands. The figure on the right shows the function that we apply. The red line shows for very low gains, we actually further decrease the gain, whereas for higher gains, we essentially leave them as is. The blue line shows what would be the identity function here. The figure 6 fitting strategy employs a loudness normalization ratio. Only threshold data are employed in generating fitting targets. Figure 6 provides targets for low, middle, and high input levels. For low input level, gain is prescribed with the goal to provide aided threshold when the hearing loss is mild to moderate in severity. For greater degree of hearing loss, aided threshold increase as a function of increasing severity. At middle to high input levels, the gain required for normal loudness perception, assuming 16.5 and 19 dB SPL input levels, is prescribed. The amount of gain required is based on average data obtained from individuals with hearing loss. Let me go on the evaluation of the system on the challenge data. Clean speech comes from the British National Corpus recorded by 14 speakers. Half of the interferer data is speech interferer, come from SLR 183 database, while noise interferer comes from free sounds database. SNR is set from -12 to 6 dB. Room impulse response is produced by real-time acoustic simulation software. The reverberant time is set to 0.2 to 0.4 seconds. Listeners are identified by their binary pure tone audiograms measured at these frequencies. The model was trained with 6,000 cents from the training data. Validation is done with 2,000 cents from the development data. Model works on 16 kHz. The remaining 20% of development data are then used for our enhancement evaluation. The final subjective and objective evaluation is done by the challenge organizers and is performed on a blind test data, which hasn't been seen before by the neural network nor the reference samples, of course. The complexity here is 35-mile floating point of operations, and the model size is 1.5 million bytes. The processing time on one frame is approximately 1 millisecond on inter-7 serials. We see both in the enhancement evaluation and blind test, the system we proposed performs better than the baseline. To further illustrate the performance of our system on the blind test set, on the left, the target is mixed with noise interferer. On the right, target is mixed with speech interferer. Let's listen to these samples.
Couldn't do it without you. Couldn't do it without you, you know. Couldn't do it without you, you know.
A wrist clasp is a mechanism made of
He
a
said
metal
we
head
had not
and a
made an
like
official
label.
request.
Production of serious plays was...
He said we had not made an official request. He said we had not made an official request.
The second line is without equalization, and the third line is with equalization. It's obvious that without equalization, some speech distortions audible, and residual noise slightly fluctuating. Equalized sample sounds more natural compared to baseline, and residual noise almost inaudible. So let me conclude. We present a cascaded general speech enhancement system. The advantages of this system include causal, optimizing for perception, and it reduces the model complexity and size. Personalized dynamic equalization scheme improves subjective perception despite hurting MBSTOI. In a word, we remove both noise and reverberation from the speech signal to improve the listening perception and intelligibility for hearing impairments. Thank you for watching this presentation. If you have any question, just contact me with this email. Thanks.